Hello dear students, I have come to you with another practical of your numerical modeling class, and we'll be using FLAC 3D. And today's problem definition is to perform finite difference analysis of a rib pillar. So you know rib pillar, theoretically you have studied in your coal mining subject that rib pillars are pillars which are left out in a panel after the panel has been extracted. Okay, so we'll be performing a finite difference analysis. And some things to notice is that the width of the rib pillar is 24 meter and it is situated in a depth of 200 meter between two horizontal panels which are 100 meters wide. I'll be showing you the geometry as well. So what do we have to study is that we have to study how the strength of the pillar is differing with the height of extraction. Okay, which means the height of the pillar will also simultaneously differ according to the height of extraction. So the height of extraction is 3 meter, 6 meter, 12 meter, 18 meter, 24 meter. So according to this, there are 5 variations of the height of extraction. Along with it, there is another thing that we have to study is that there are 2 property sets that we will be applying to the pillar strength, or we'll add one more immediate floor to the model. And there are 2 property sets which are given. Property set 1 is one variation, set 2 is another. So as we go on, you will understand what it is. So just to explain simplify the problem in a visual way, I have made a model geometry. Here it is. This portion is the roof, which is 200 meter. And then the rib pillar is situated 200 meter below the roof. This is the panel 1, which is 100 meter width, panel 2. And the whole length of this in the longitudinal direction is 400 meters. Here you can see. And so if panel 2 is 100 meters, panel 1 is 100 meter, rib pillar is 24 meter wide. So we're left out with 88 meters along both sides. And the floor is again 100 meters. And so and this point, black dot that you see, is the origin. H is the height of extraction, or you can say the height of rib pillar, which will be varying, as I said earlier, 3 meter, 6 meter, 12, 18 and 24. Okay, and what we can do is that, since if we pay close note to the origin, it is right at the center and there is symmetry on both sides. So we will first make the symmetrical geometry, and then there is a FLAC 3D command which if you put that command, it will reflect the one half of the pillar and again construct the other half automatically. So that's the good way to put it. Again, as I said, there are different variations of property as well, material property. So pillar rock has these properties, which is UCS 5 MPa, tensile strength 0.6 MPa. So since we are going to use more Coulomb strength criteria, so you will have to have tensile strength as an input parameter. Okay, so we have UCS 5 MPa, tensile strength 0.6 MPa, and angular vertical friction 30 degree, modulus of elasticity 2 GPa, Poisson ratio 0.15, density, and then the roof and floor have the same properties. This is property set 1. There is another set which I told you, property set 2. There is one addition, which is that we will be adding an immediate floor here of 2 meter, and this floor will have this property set 2. Rest all will remain same. So you can subtract 100 meters from 2 meters from the 100 meters. So 2 meters immediate floor and 98 meters as the other floor, bottom floor. So the roof, pillar and floor, bottom floor will have the same property set 1, but the immediate floor, which is an addition, will have modulus of elasticity of 0.2 GPa and Poisson ratio 0.25 and density 1700 kilogram per meter cube. And the other things will be same as the floor property. Okay. So again, we'll be activating the gravity loading. Since we are modeling the whole 200 meters, if you activate the gravity, the vertical stress will keep changing according to depth. Okay, if we don't activate it, it will be the same everywhere. Next, so the steps I'm going to show you in the video, and follow it very carefully. I have done, this is the observation table, and you can see that we're going to observe the sigma 1 value, maximum principal stress, because this is going to be used to find out the factor of safety. Here is the Mohr-Coulomb equation. Strength, which is sigma 1 equal to CO, which is compressive strength, plus Q, sigma 3, where Q is equal to this value. Okay, so sigma strength is the maximum value of strength is the maximum value of sigma 1 where the pillar fails. So we'll be finding it in two different places. One is the center of the pillar and the other is at the pillar edge. So this is the center and at the pillar edge, and we'll be noting it down in this observation table according to different pillar height: 3 meter, 6 meter, 12 meter, 18 and 24. I have done some of them, rest you must do it, and carefully follow the instruction that I am going to show to you in my FLAC 3D software. So here we go. I have done two things. There are various ways to model this whole geometry. One would be to take here 0 origin and then 400 meters, and on the top calculating the height, total height. This is 100 and this is if 3 meters and this is 400. You can go like this, and y direction will be unit length since we are doing a 2D exercise. So that could be one form, and then giving same mesh size everywhere. Earlier in the first tutorial I explained what mesh size is, but what we did in that way, we'll have equal mesh size, but the number of zones will increase. If we keep the mesh size as 1 meter everywhere, then this side 400 meter will have 400 zones. Again, this side will have 200 plus 100, 300 plus 3, 303 zones, and other side 1. So if you multiply those three, you'll find the number of zones, and that will be significantly high if we keep the mesh size equal everywhere. And the computational time in our laptop will take almost a day to solve it, and I've tried it and I saw that it's really getting difficult. One problem cannot take 1 day. So there is another way way that we can model this geometry, is that only keep the mesh size of the area of our interest, a finer mesh, which I have kept 1 meter, and as we gradually go to the boundary, the mesh size will keep on increasing, and it is a geometric progression. So it will happen gradually. It would not happen abruptly so as to affect the result of the model. Okay. So that's the one of the benefit in FLAC 3D, and so we will do it. Let's go to the let me show you how we can do it. So I'm using FLAC 3D 6 version 6, and this is the way it looks. And when you open the FLAC 3D, it won't look like this. It will be blank, and you will have to enter, and one dialog box will appear as create new project. So you'll have to click create new project and save it on a folder. And then if it doesn't look like this, as in the data files are not here or saved states area is not here, result file is not here, then you can go to layout, and select the wide layout. Okay, you can use the wide layout, and then it will look like this. So first thing is to save the project, and then everything that you make changes in the in your model, it will get saved to that same folder, same location. So first Second thing is that you have to make a data file. The data file will contain all your FLAC 3D commands, which you will write it down, and then when you run it, the results will be saved here. Each model will be saved here. These are the data files. You can even use a notepad, but I recommend that you use the data file which is already in the FLAC 3D. Why to do it externally? Both the functions are same, but you'll have to do an additional command to use a notepad. So how do we write a data file? So first of all, you'll have to go to the file button here and then click on it, and here you can see add new data file. So when you click on it, this is the folder where you are saving it, and then you can write the name of the file, anything, and then open it. So as you click it open, it will open up. Now this is the data file. It's not very difficult, it may look daunting at the first instance, but when you get a hang of it, it's fairly easy to do it. Once you make the geometry, things become very easy. Okay, so as I told you, we'll be creating half portion and then reflecting it back to the other half. So we'll just create the left half portion. Okay, so this portion is the one we are creating. This is origin, so this is the x direction. We are taking x as the longitudinal direction and z as the vertical direction and y as the transverse direction, which is unit in length. Okay, so if you calculate the length of the longitudinal direction from the origin, it is 12 plus 100 plus 88, which is 200 meters, right? Already it's 400 meters, so one half is 200 meters. So we'll be going backwards, left half. So if this is origin, this will be minus 200. So yeah, so we are using brick element, and I have already told you what brick element is in the last class. So there are three portions to the model. One is floor, one is coal seam, one is roof. And we are giving this command. We are creating brick, and these are the number of bricks that are going to be used to cover that whole length. Suppose we are starting from point 0, which is minus 200, 0, minus 100. Whenever we are making a geometry, we will start from the bottommost or the sidemost coordinate. So since we are taking the left half, we are going to the negative direction first. We are making the boundary first, because this is origin, so this is going to the negative direction. We'll start from the floor first to model. Otherwise, your geometry will not be found properly. You have to follow in order. So minus 200, 0, minus 100 is this portion, this point, and this is that point, and then point 1 is going to the x direction. So x will be this point here, which is minus 12. We are not going to the origin, because as I told you earlier, this portion is my area of interest, the rib pillar. So this half I will model it with a mesh size which is 1 meter. The other half I'll keep on increasing gradually, so that my number of zones may be less, so that my computational time may decrease. So point 0 to point 1, I am using 47 zones to cover around 188 meter of length. Okay, and then so point 0 to point 1 is towards x direction, point 1 to point 2 is towards y direction. So here x is changing. If you see point 1 to point 0 and point 2, you will see that only y value is changing, and then point 3 is towards z direction, and point 3 the z value is changing, which is 0. So if you give this command, run it, you can select this like this, and then right click and run selection. So only one point only this command can be executed, and then you can see the geometry what this command is creating in your plot tab. Okay, but I have done it already, so I'm showing you. Next is this ratio. I told you that I am using this ratio command is basically setting the ratio number of zones, what will be the length of the number of zones, and how will it gradually increase or decrease according, and it follows a geometric progression. You know geometric sequence, that there is a common multiplier which will get multiplied to each number of each element. Suppose the first, suppose I keep here 0.951. The first zone will be of a certain size. The next zone will be 0.951 into the length of the first zone. The third zone will be 0.951 into the length of the first zone. Sorry, the second one. So that is how it will gradually keep on increasing, right? So in the x direction I have kept 0.951. Why 0.951? Because I am starting from here. So I am basically following a descending order. The first zone here will be the largest, and then it will keep on decreasing. If you have to make this one as the finer mesh and keep on increasing in this direction, so you have to place an input of a value of ratio greater than 1. Okay, if you keep it 1, it will be suppose I am covering 10 meter of length with 10 zones. So if I keep a ratio 1, then the 10 meter will be covered by 10 zones of equal length. Each zone will be of 1 meter. But if I put it 1.1, then each zone will be a product greater than the previous one, 1.1 times greater than the previous one. Okay. If I keep it 0.9, then the first zone will be the largest, and gradually it will keep on decreasing to the 10th zone. I hope you understood it. If you have any doubt, you can put a comment in the YouTube video and I'll be addressing it. Probably I believe that Professor Budi is going to make a common discussion amongst us, so that I can explain you in a much better way. So how did I choose this number 0.951? So mathematically I will do it. I did it in my paper. I wrote the sequence, and how, if the length is 188 meters, and if I'm keeping the number of zones as 47, what should be the ratio, so that the zone which is near to the pillar is approximately 1 meter, and the other ones are also almost 1 meter of length which are nearby. So I got the number 0.951. I have made an Excel sheet and put the formula so as to know what should be the ratio. Okay. If you need it, I can send it to you. So this portion, as I told you, is only this part, from the edge of the pillar to the end of the model on the longitudinal direction, and then we will this part of the floor. Okay, and then we will model this half also, the 12 meter of the floor. So this is the command. As you can see, I'm using 12. Since that is the rib pillar, I'm using 12 zones to cover 12 meters. As I told you that I will be keeping the mesh size as 1 meter. Okay, and I grouped both as floor. The same way, I am now modeling the coal seam, and you can find the coordinates. This particular seam is modeled till this portion first, and then the pillar 12 meter. Okay, and one thing to notice is that the height of the seam is 18 meters. I have kept 18 meters, so I wrote the name as 18 meter, geometry 18 meter. And the rest portion here is the roof. This should have been 218, but there was a small mistake. However, it should not disturb or alter the result much, but this should have been 218 because 200 meter is the length of the roof. So from the origin to the height of the pillar is 18 meter, the rest 200 should be 218, the topmost part of the model. So that's it. You can rectify this, and then again ratio and group command. I've explained all of this properly in the first tutorial. You can watch it in my YouTube channel. So this is how we get the first portion, one half of the portion of I can still select and show you if I run this how it would look like. So if I run this, you see that this is half of the portion. So each have become grouped. This portion is the floor, this is the roof, and this is the cold seam. Okay, this is the left half. And so the other command is creating right half of the portion of the model. So I use the reflect command to make the right hand portion of the model. So if I run this, you would see that these many grid points and zone security. Grid points are nothing but can be said as nodes of the zones. Okay. So now you see that my geometry is complete, and this look a little bit darker since this is a finer mesh at 12 meter, and this portion also in the cold seam, near the cold seam, the mesh are finer, so that our area of interest will have fine zones. This is how it looks like. And then we use this zone attached by face. So we have created different groups, roof, floor, and seam. Just to make sure that all these groups are attached together and may work together, we use this command zone attached by face. So when you run this command, and if you see that, you will see that it will tell you the number of faces that are found, and it will tell you whether how many grid points are attached. If 0 grid points are attached, which means that all the faces are already attached, and that's why there was no need for any more grid points to be attached. If it will show any number of grid points, that means your geometry has grid points which are not attached, and there is some sort of difference in your in the geometry of your roof, seam, and floor. All the three are not having same alignment, but depends on the geometry. Some of the geometry will be complex, and you will need to attach them. So it doesn't mean that if they are not aligned together, then your geometry is bad, but it is necessary to attach them. Okay, then we save the geometry, and yeah. After making the geometry, the first thing that we do is we assign the material properties for each layer. As I told you earlier in the first model, I told you that Young's modulus can be put by Young's modulus and Poisson's ratio are two things that we don't put directly. But after going through the FLAC 3D manual, I found out that Young's modulus and Poisson's ratio both can be given as an input directly into the model, because previously in other versions, previous than FLAC 36, those were given input as shear modulus and bulk modulus. If you give this to input, the software will automatically derive the Young's modulus and Poisson ratio from these two values. But now I saw that you can put an input directly. So as property set 1 says, density to 2200 for roof and floor. Roof and floor both have same input properties. Only the seam has a different input property. Moreover, we use this command zone C model assign more column. We are using more column failure criteria to model the behavior of the of our model geometry. So the inputs are density and modulus, quantity of friction, cohesion, and tension. Okay. So you know that we need cohesion values for a Mohr Coulomb equation, because this value right here, C naught, called UCS, is a function of cohesion, 2C cos phi divided by 1 minus sin phi. So since I know the value of UCS and I know the value of phi, I can get the value of C, because 2C cos phi divided by 1 minus sin phi is equal to UCS, right? I have the UCS values, and so I derived the I produced the result for cohesions by using that formula, and I have put them as input here. The next thing is that we initiated gravity. I told you the reason why earlier. And then we are applying boundary condition, which means we are constraining the bottom in vertical displacement, that this should not move vertically. This bottom should not move vertically. They should act as a reaction force to the forces coming from above. We put roller boundaries here in x direction, and in y direction also we have put roller boundaries. These are the commands which I used to put roller boundaries. Zone, phase, apply velocity in z direction at the position, range position z minus 100. The bottommost position minus 100. And topmost is kept free, and this is in x direction at minus 200 meters, and this side at 200 meters. We are restricting restricting displacement in x direction, and then in y direction also in 0 and 1. So if you want to see whether these have been applied to your model or not, you can go to your plot tab and right click on it. You can click on add plot item, and then you will see GP fixicity, which means grid points fixicity condition. When you click on it, it should come. I don't know why it's not coming. However, let me try again. I don't know what's wrong. However, let's go ahead. But these commands are correct. I have used it. Maybe my computer is malfunctioning. Here next, what we are doing is that we are, since we made this model, in the coal seam I'll be making 3 groups. One is the rib pillar, the other is panel 1, and other is panel 2. And panel 1 and panel 2 are 100 meters width, and pillar is 24 meter width. So I use this command zone group rib pillar, and I put the position in x direction, y direction, and z direction. So all the zones falling under these this range will be grouped under rib pillar. Okay, and then similarly I used it for panel 1 and panel 2 also. You can look carefully and understand the coordinates of these by looking at the command carefully. After I have grouped the rib pillar, panel 1 and panel 2, the stress condition are already given, boundary condition, by activating gravity. There is no horizontal stress as such that has been mentioned in the practical, and the vertical stress is derived by its overburden, so gravity is activated. Now we solve the model. We put this command model solve, and then it will solve. And this is the initial solving, where the model is created. Excavation is not done yet. We have just created the model and we are solving it. After solving it, the model will come into equilibrium state, and then we are going to save the equilibrium state, model save, virgin geometry, and then I make the displacement as 0, 0, so that there may be 0 displacement anywhere in the model before excavation. and then I excavate panel 1 and panel 2 by using this command zone delete range group panel 1 and zone delete range group panel 2, and then I solve again. Now when I solve it, it will go different cycles. Then the number of cycles will be here. It will be running in this console area, and then as it solves, the displacements and the stresses will be updated, and once the cycles are over, you will get the results, final results, and then you can save the model as model say final 18 meters. So you see I have saved it in three instances. Saved the model 3 instances. One when I made the geometry first, then after solving the initial equilibrium, I called it working geometry, and then I put after excavating and then solving it again, I saved it as final geometry. Okay, so let's get into the result part. Before that, I would like to show you one more thing, is that once you solve for the initial equilibrium, you can check out the stresses here by clicking at zone group and then go to level, go to contour, and check the stress. So this is final 18 meter. If you have to check the stresses, you go to this, activate this, select contour, in value select stress, you can, and then go to ZZ. This is the vertical stress. Click this button to reset it, reset the view. This is panel 2, which is extracted. This is panel 1, this is the rib pillar. And when you have to, I told you to check the stresses in initial equilibrium position, you can go to your virgin geometry I don't know yeah, so this is virgin geometry. My computer is lagging a bit, and when you do the initial solution, this part, which I mean this part, solving the initial equilibrium, then the stresses will look somewhat like that, equally graded in different colors. The bottommost will have the highest stress. You can see here minus 6.3 MPa. Topmost will have lesser, minus 0.1 MPa, and almost 0 at the top. Okay, and it will keep on increasing as we go deeper and deeper. This is the color grading which you should find. If this is not so, then your model is not in equilibrium position, and after we excavate it, the stresses will get disturbed, and then you can see where the stresses are concentrated. So wherever the blue color will be there, the stresses are concentrated. So now after excavating this, we are going to see the result. I have saved it as final 18 meter. Yeah. So look at this portion. This is zone ZZ stress, which means vertical stress. I told you already how to activate it from this 3. And you can observe that these red colors are 0, which means these have failed and these stresses have nulled here. And the stresses have gotten transferred to the center of the rib pillar. and this area is also carrying less stress because this is in a failure state but still intact in the pillar. This core is still intact and it is carrying the load, and the stresses have concentrated in the pillar in the center, and there are certain concentrations here also, blue color. So you can see the grading of the stresses here according to the color, right? So these are some way to interpret the stress. Our interest is to get the maximum principal stress and then use the formula of Moore Coulomb to find the factor of safety of the pillar. So there are two areas where we will get 2 points in the pillar where we will be observing the maximum principal stress and then noting it down on our practical sheet. So I will change the stress to minimum principal stress. In minimum principal stress, the maximum value is the maximum one, and the red portion is the minimum principal stress. Okay, so here we see that the maximum principal stress is in around the center of the repeller. To remind you, this is 18-meter height of the repeller. So we're going to go to the center. If you put the cursor nearby this area, you can check the coordinates which will get updated. Here location you can see, and the value will be shown here. Okay, and it will show you some information which group it is in, which group your cursor is at, and where your cursor is hitting. So location, by location you can know that since it is 18 meter, the center would be 9 in z direction and 0 in x direction, because 0 is the center. So you can see I am right at the center. You can see the location here. Just check it, 009. It should come 009. Yeah, and then the value, it is showing minus 1.55 E07. E is 10 exponential 10 to the power 07. So it is around, and minus sign is obviously showing that it is compressive in nature and in the negative z direction. And so here you see it. So it is 15.5 MPa. Okay, minus 1.55 means 07 means 15.5 MPa. So I'll note it down. And then we go to the edge, and it should be minus 1209, and it is around minus 4.8 MPa approximately, and I have noted it down here in my practical observation table for 18 meter, 3 minus 15.5 and 4.8 MPa. Okay, for set 1 property. So this is all for this one. Again, I'm making different data file for set 2, where I'm including one more immediate floor which is 2 meter of height. As you can see, you can use this command to make 2 meter of height. And then if you look closely, observe it, then you will be able to know how I have created it. I've already explained in detail earlier. So only addition is the immediate floor, which is 2 meter of height. And then again, the addition is the properties of set 2, which is given here. Only density, Young's modulus and Poisson ratio are changing. Rest all are same as the floor 2, which is property set 1. So the boundary condition and everything is same. And as you solve the model, and you can see I have again solved it and named it set 2. I'll go to the final result. You will see that model restore final 8 meter set 2. So this is where you see whether it has activated or not, and you see that set 2 is activated. And let's look at the values of maximum principal stresses. In the center, you can scroll in your mouse to go towards the center. Put your mouse near the center and then scroll it, so that portion will be zoomed. Wherever you put your cursor, that portion will be zoomed. Okay, so you put your cursor here and zoom it, and you go to the center. So I'm at 0, 0, 10. Go to 0, 0, 9, and the value is minus 1.3933 exponential 0.7. So it is minus 13.9 MPa, and this at the edge is minus 4.87 MPa. So as you can see here, I have written minus 13.8 and 4.9 MPa. So you can see at the pillar edge there is not much difference in the strength, the maximum principal stress in the pillar that is occurring in the pillar edge, but at the center it has decreased. As we have introduced a new soft floor, it has decreased. Okay, and the other thing is to do is find the sigma 3 value also. So I'll find it, and then you can go ahead. Go to the maximum, and then at 0.09 you will see the sigma 3 value is minus 3.49. Here it is showing minus 2.9796, which is approximately 3 MPa. So I will write here 3 MPa. Sorry, it was set to, so 3 MPa. And at the pillar edge, it is 20,578, which is 0.2 MPa tensile in nature. 0.2 MPa tensile in nature. It's not 0.2 also, it's 0.02 MPa. 0.02 MPa tensile in nature. 2.02 MPa. Okay. Let me find it for set 1 also. Set 1 is loaded, and the center part is showing minus 3.5 MPa, and the edge is 0.04 almost. Minus 3.5 minus 3.5 and 0.04. You can put minus here to show that these are compressive in nature. The positive ones are tensile. Now get the strength sigma 1 value using this formula. Okay, you know the C0 value of the pillar, UCS value. Put UCS here and get Q from here. You know the pi value here, and sigma 3 is here. This is sigma 3 value. Multiply it, get the strength in set 1 and set 2, and then you find the factor of safety by dividing the strength by the stress, the sigma 1 value. See the factor of safety of the pillar, and get the weighted factor of safety. Okay, make an average, and that will do for you, I guess. And don't forget to put minus wherever it is compressive in nature, as you see in the FLAC 3D software, so as to not confused. I have made so many models and I've already solved and gave some input. The rest all things rest you can do on your own, and you can look at the tutorial carefully, follow the commands and make it, prepare it, and then you are done with it. So thank you for listening attentively, and I hope that you will be able to make these models properly and you will become friendly with the FLAC 3D software, and you may use it in the future for your research and other things. If any doubt, you can comment in the video, or perhaps we may have an interactive session very soon. Yeah, thank you so much. Bye.